for providing this for us. I also want to do a quick thank you to Alpine for providing people for check-in and such like that. Now I'd like to introduce our speaker, Nasser Manesh, and his talk is on running production Hadoop clusters in Docker containers. And he is actually the perfect person to be talking about this because of what he does currently at Altiscale. And what does he do? Well, he has spent the last year putting Docker containers into production. In addition to that, he's also working on the orchestration of moving these containers around within the infrastructure. So again, he's perfect for this talk, and he's going to share his experiences with us. On the non-technical side, I just found out about him that he was one of the people who brought the Cyrus cylinder on tour from England to the United States, so we may ask about that before you start talking about Docker. So welcome, Nasser.
Thank you very much. Let's make sure that this works. Good. Well, first of all, thank you guys, Alpine Data, Yelp, for hosting, arranging this. This is an amazing opportunity. Cyrus cylinder, 2 minutes, just since you asked. It's one of the old artifacts from about 2,500 years ago, excavated by the British Museum. And I was fortunate to be part of the team that arranged a tour to bring that from the British Museum to a number of museums in the United States for about a year for the first time. It's called the First Declaration of Human Rights, and there's a long history around that.
Where did you come from? Where was it from?
So I'm originally from Iran, and it's in old Persia, which is now Iraq. So it was excavated from Iraq. That's where things started. All right, but we're here to talk about Docker containers and production and all the good stuff. A little bit about my technical background. It's very nice outside, so I do appreciate the fact that you guys are letting that go and sitting here listening to me. So let's hope that I can deliver something that is useful to you. I'm currently the product lead for orchestration service at Altiscale, where we do Hadoop as a service. I've done for pretty much all of my professional life, I've lived on Unix before Linux was around. So I've done infrastructure, systems administration, SRC, kernel stuff. I launched a couple of startups. I've been in VP of engineering and CTO roles. Right now, it's been a while that I've been focused on large-scale distributed systems, specifically Hadoop clusters, petabyte scale, and how we do virtualization, how do we do elasticity and making these clusters bigger and smaller sort of in real time based on customer needs. This is my email address if you want to connect with me on LinkedIn. And we will be talking about something that is kind of not common for some strange reason. Docker is hot these days, right? Everybody talks about Docker. But you do not find many companies that are using Docker in production, or you do not find many people that are working on putting Docker in production environments. And we'll be talking about that, which sort of I spent a year of my life on. Before we do that, a show of hands so that we get a feel of the audience. How many of you are in operations, DevOps, systems administration? Wow. Oh, OK. I almost started with none. We have 4 or 5. OK. Developers? Most of the audience. Perfect. Users of big data, data scientists? We have quite a few. Not bad. Management, product managers? OK. So this is actually the typical mix that I've seen. I have delivered this talk. Obviously, it has developed over time, but probably 4 or 5 times now over the course of the past 6 months. And typically, this is what we see. Most of the audiences would be developers, and then a few DevOps, SREs, a few data scientists. Actually, there are more data scientists in this audience right now compared to what I've seen before, and some people on the product management and management side. So let me tell you a little bit about what we do so that you get a feeling of the problem that we were trying to solve. So at Altiscale, we provide Hadoop as a service. Customers use SSH or browser to connect to a machine, which is where they run their applications. And these applications, this machine is connected to a Hadoop cluster, which from their point of view is totally theirs. They can do everything or anything they want to do on it. And there are all the typical Hadoop components, the name node, the resource manager, and all the Hadoop slaves. And the applications that are launched here are distributed onto the cluster. And the data that is ingested by the cluster goes onto these nodes and goes to HDFS, replicated, all the good stuff. Now, the customers, you can think of us as AWS, but not providing generic computing infrastructure. We provide distributed computing infrastructure. The first-class citizens in our service are HDFS and slot hours, compute hours, right? So when you upload data to an Altiscale cluster, it goes to HDFS. There is nothing like S3 or EBS storage or any of that. You don't see storage in the typical sense. You see HDFS. And when you're running jobs, you don't think of nodes. You do not bring up nodes. You see a cluster. The cluster lives there. If something happens to the cluster, it's our code and our staff that takes care of it, and that cluster heals itself. And to you just keep running your job. So it's a distributed environment as a service for the customer. Now, we do this on bare metal. So we manage our own data center space, typical setup, East Coast, West Coast. We have to pay for the power, for rack space, and for the machines. And even though the legend says that Hadoop machines are commodity hardware, that's relative. When we say commodity hardware, if you want good hardware for Hadoop, you still have to have the type of machine that runs anywhere from 40-something to 256 gigabytes of RAM. Typically, the machines have anywhere from 8 to 12 hard drives. The components are picked so that you can do things at high throughput. For example, we use a type of controllers in our machines that can operate all of those 12 disks in parallel at maximum throughput. These are important things to Hadoop because it's big data. You want to be able to write a lot of data at the same time and read a lot of data at the same time, which means it's expensive. So even though this is commodity compared to some premium hardware, when you multiply the number of racks and all the space, thousands of nodes, this is expensive stuff. So for us, the margins of the business are directly related to how well we can optimize the way we are using these resources for our clients, right? So if we have a machine that a customer is currently not using, and that machine is sitting there idle, that's cost to us, right? Ideally, I would want to run some other customer's job on that machine, but then you run into the issues of security and isolation and all of that. So the question of how we, as a company that runs bare metal, how we partition and reallocate physical resources is key to the profit margins of the business. So how can we go about this? Hadoop itself as a distributed operating system, if you want to call it, has built-in capabilities to slice and dice things. However, the multi-tenancy side of Hadoop is not really all that well developed. It's not enterprise grade. And as you can imagine, the type of customers that use an environment like this are enterprises. So they care about security. They care about the fact that their data should really remain their data. Nobody else should see that data. Nobody else should see their jobs. Nobody else should see their names. So that's important to them. And you can achieve some of that with what is built in Hadoop, but not all of that. Actually, it's far from what you would call ideal. Or you can go the traditional route of using hypervisors, right? Build virtual machines and basically partition these machines into smaller machines and allocate those to the containers. However, and virtual machines and hypervisors have come a long way. But when you think about us running Hadoop jobs, which really, really drive these machines, a typical machine that you look at in our environment is maxed out. You see jobs that on that 256 gigabyte machine constantly run out of memory. You see cores that are at 90+% busy. So if you're running a hypervisor, which is taking some of your memory and some of your CPU cycles, for one machine, probably it's not that much, you don't care. When you multiply that by 1,000 machines, then you're really paying for running that layer. Those are CPU cycles, and that is memory that you could have used for a customer job. So it's cost. Which brings the third option, which is kind of the focus of this talk. How can we do some sort of lightweight virtualization? And this is where containers are a good candidate because they do not take as much memory as a hypervisor. They do not take as much CPU cycles, so you can still use your machines almost for your customers, but you get some of the benefits that we're looking for. So what does a container really give you? How many of you have seen The Truman Show? Half. It's a really good movie. And Jim Carrey is living in this world where he doesn't know that it's virtual, and he's living his life, but some people are actually watching him from the outside. That's what containers give you as isolation. Isolation, the beautiful thing about isolation is that the process that is running in isolation doesn't know that it's isolated, which is in contrast with resource limits, which is another important aspect of this, where you put caps on things that a process can use, but the process actually knows that. If it tries to sort of allocate memory beyond a certain limit, it will fail. It can actually query to see how much memory it has, and it will know, right? So resource limits are things that the process know. Isolation are the stuff that the process doesn't know. We just contain that. Now, in the Linux kernel, isolation is implemented through namespaces, and resource limits is implemented as C groups. And for the longest time, these two were kind of sort of two different concepts, actually developed for two different reasons. But at some point, these two converged into what we now call containers. So let's look at how things actually run on a machine when we have hypervisors versus when we have containers. And this will give you a good idea about why that overhead exists. So when you are running hypervisors to virtualize a machine, this is your hardware, and you run a host OS, typically Linux. Nobody runs Windows, right? Okay, good. So you run something on top of your Linux, and this thing, the hypervisor, gives you the virtual machines where each of those machines is running a guest OS. So technically, although you wouldn't want to do that, you can run Windows here, right? And you can run Mac OS here, and you can run Linux here. So you have, effectively, you have 4 kernels running on this machine. And then your applications on top of this guy, you have applications on top of this guy, you have applications on top of this guy, totally isolated, they don't see each other, and all the good separation that we were looking for. In the case of containers, those two features that we talked about, isolation and resource limits, are the features of the host OS, right? So it's this OS equal to this guy that is doing the magic for you. It's doing the isolation. It's doing the limits on the resources that other processes can use. So your applications are still running on top of the host OS. There is no guest OS. This is where that difference in terms of the CPU cycles and the memory and all of that comes from. You do not allocate kernel memory for 3 other kernels. It's this guy just putting the walls across these processes and giving them limits and so on and so forth. And you might, although we're not still talking about Docker, but since I stole this picture from the Docker website, there is a Docker here. And you might notice that this line is drawn here and not here. Docker, as we talk about it more, doesn't do anything kernel related. Docker is not containers. Containers is the implementation of isolation and resource limits in the kernel. Docker is a tool that lets you play with that, lets you set things up with those features. So Docker is not in the kernel space, it's just a user space program and the tools around it. Which means it's one of the ways that you can create containers. It's not the only way. Actually, if you look at the history of how these things shaped up over the years, many, many, many years ago, we had CHROOT, and we still have CHROOT. How many of you are familiar with CHROOT or used CHROOT? A few people. So from the old days, you had this capability in the Linux kernel where you could limit a process. This is isolation. This is not resource limits. Where you could isolate a process so that it only sees a certain subset of the file system. It thinks that that is its world, right? That directory becomes the root of that process, and that's it. It doesn't know of anything outside of that root. So that's where things kind of started, which is very interesting, but obviously it's not enough. It's just isolation around files. Then back in 1995 in BSD, people implemented jail, which is a better sandbox. It actually has networking isolation, but there's still a lot of limitations around it. And then you see that Linux vServer was implemented. Solaris, the Sun guys, who were the sort of the forefront of bringing a number of different innovations to the Unix kernel, implemented Solaris zones back in 2004. I think it was Solaris 9 into 10. OpenVZ came about, and then LXC was kind of probably the most mature implementation of what we just talked about, isolation and resource limits. And by 2007, actually coming out of Google, Paul Manoj unified these into the Linux kernel. So containers have been around for quite some time. And interestingly, many of them are very, very robust. LXC is very robust. BSD jail has a very advanced and nice design when you look at the current kernels of BSD. LMCT5, which is short for let me containerize that for you, comes out of Google. So it's Google quality. That's actually a subset of the things that Google was using at the time for putting containers on their machines. Google heavily uses containers. But the problem with all of that was that they were hard to use. You have to be like a real geek in the Unix world to know how to set up a container and how to set up LXC containers and how to operate them and how to make changes and all that. A lot of command lines. You needed and you do need to have some kernel knowledge of how these things work. Otherwise, you're like in this endless mess of things that do or do not work, and you don't know why. because it's complex. What Docker did, to their credit, is that they made it really, really easy to create containers. Everybody can do it. 10 minutes, tops, right? Boom, 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 you run a couple of things, you download a couple of things, and you have containers on your machine, which is amazing. It's kind of the Apple way, right? You don't have to think about things, and you do a few things, and it just works, which is great. There are some very interesting use cases for Docker. We were actually just talking about that before this talk. So Docker is really great for doing local builds. If you're a developer on your machine, you want to run things on your machine and test them, or if you want to create pipelines that launch little machines to test something and then they are destroyed. The fact that Docker lets you package things together, which actually I must have on this slide somewhere. Yes, here. So Docker gives you this is where I was saying Docker is a set of tools, and it has nothing to do with the kernel really. As a part of those tools, one of the things that Docker gives you is the ability to package layers of software to deliver them as what they call a Docker image, right? It's pieces of software nicely laid on top of each other, which you can deliver like an RPM to a host that is going to be using that. So the fact that it gives you that kind of capability for nice packaging makes it easy to package things in environment A, and ship them to environment B and run it there. So it's good for doing testing in different types of environments. If you're doing like Jenkins integration kind of jobs, slave machines, because they are kind of, they come and go. They launch, they do something, and they finish their task and they're gone. These are all good cases where Docker works nicely. There's a big yes, but. Oh, man. When it comes to production environments, yeah, it's my problem now. It doesn't really work nicely in a production environment. And there are reasons for that. First of all, when you deal with a production environment, most probably the reason that you're using containers is that you want a lot of them. If you are having a production environment with 2 containers, hey, come on, you could just put 2 machines there and you're done, right? But if you're dealing with thousands of containers, you need orchestration. You need to be able to define workflows in terms of when I want a container launched, when I want a container to start, when I want it to stop, when I want it to be taken out of the cluster, and so on and so forth. There's no orchestration tooling around container. Things are changing, but for the longest time, there wasn't any. Provisioning, creation of containers in a production environment requires things that do not come neither packaged nor easy with Docker. And there's no automation around it. So if you follow a set of instructions for doing things on your laptop, great, it works. But try to do that on a machine where you have console access through some weird network and VPN and all that, and you want to launch things, not as easy. When you run things in production, the first thing that you want is to be able to troubleshoot problems, right? Things go wrong, you want to look at logs. Good luck. The first thing that we ran into, actually, which was amazing, was that, so we launched these containers and we were doing stuff and something went wrong, and we go to /var log, look at the log files, and there's nothing there. Like, why? How could that be possible? Go to the other container and no, there's nothing. So finally, we found out that everything was going to the var log messages on the host where these containers were running. And guess what? They were just intermingled, and good luck finding the logs that belong to container number 10 running on that machine. because the separation of the log namespace is not well implemented in Docker, which makes it, just that alone makes it a no-go for me, the ops guy that gets paged at 2 o'clock in the morning to fix a problem. Networking. So in environments like what I described to you, where you are running a heavy enterprise grade network of machines, you want your network to be high throughput, very robust, which means typically you run jumbo packets for large Ethernet frames because it's Hadoop. You're pushing data with high throughput. You want very fast and very reliable routing, which means that typically you run something like OSPF. You don't run RIP for your routing. And then you do BGP to do things across your networks and all that. None of that works nicely with Docker. What Docker does is that it takes over your host and allocates IP addresses from a given range, a very private range, and those containers live a happy life among themselves, and it's a happy nation. But it doesn't work well with the United Nations, right? There's no channel of communication. Most of that kind of boils down into this statement, which I think is very, very important. When the folks at Docker.io wrote Docker, what they were thinking and what they are sort of pitching as the typical use case of Docker is short-lived containers. You launch it, you run something in it, and you dismantle it, done. You need to run something else, you launch another container, and you do stuff in it, and then you tear it down. If you need to run a container for a longer period of time, meaning that it's going to be around and it needs a static IP address, God forbid, and it needs to report back to the mothership over an extended period of time, things will go very strange ways. And the reason for that is that a number of race conditions arise when you do containers, and I'll talk about that on one of the other slides. And it sort of it goes head to head against some of the audit and security capabilities built into the kernel. So things that we really care about as operations people, which cannot be easily done in the world of Docker, are these, and I'll be talking about how we sort of went about some of these things. We need stability and reliability, and especially predictability, which is something that you cannot get when you have race conditions. Performance and security are important. Networking, we talked about. Metrics and monitoring. Docker by itself does not give you any facilities for collecting metrics. But if you're running a serious production environment, you do care about how things run. The only way to understand when things are healthy and when things are not healthy is to have monitoring and to have metrics collected over time so that you can graph things, right? And then you analyze those graphs and see when things are going wrong. Docker does not give you anything around that. But when you build a machine, there's a whole slew of software packages that do that kind of stuff for you. The delivery infrastructure, which is what is called the Docker registry, is another interesting animal. Again, it's very nice when you're doing very simple stuff. You have a Docker image and you want to deliver it to a laptop, the Docker registry works for you, great. But try to do that in a more complex environment and things go wrong, and I'll tell you more about that. And of course, logs and being able to troubleshoot and all that. So let's switch gears for a moment, now that we kind of know some of the issues that in general are prohibitive in terms of using Docker in production, let me tell you about the specific case that we were trying to solve, which was running Hadoop using these containers. So we had two approaches in front of us. One approach, when you want to do isolation, which kind of actually goes nicely with the type of usage that I just described to you in terms of what the Docker IO folks want you to do, meaning short-lived containers, is to let Yarn, which is the resource allocator and the resource scheduler of Hadoop, run things in Docker containers for you. Those of you who are familiar with Hadoop, you know that Hadoop launches what it calls containers, which has nothing to do with the Linux containers, to do bits and pieces of the jobs. So what if we could ask Yarn to launch Docker containers for us and then get things done in those Docker containers so that we have the type of isolation that we're looking for? It's actually a very valid idea, and it would work nicely, especially because not only it gives you isolation, it also gives you software delivery. I mentioned to you that Docker can package things for you. So this means that if a part of the job that you're running on your cluster requires a, let's say, Ruby gem at version 3.0.5, and it happens that another part of it requires a gem at version 4.0.0, which you can't do today, you could do that because they would run in different Docker containers, and each of those Docker containers would deliver a different version of that gem to the application that wanted to run. So good. There's always a but. Doing that requires changes both to Yarn and to Docker. And we have been working on this for a long time. Actually, as I'm talking to you here, a colleague of mine is in Brussels at the Hadoop Summit presenting the work that we did on the Yarn side to enable this. So that part is at least at the experimentation level, it is showing signs of life. If you're interested in the details, this is the Jira on Apache website where all of the details of what needed to be changed in Yarn documented. So that work is in progress, but it's going to take a long time. This is not something that will be available 2 months down the road or 6 months down the road, probably not even a year down the road. It's not production ready. It's getting there. So in a way, it's a nice idea, but it's just, theory. It's not going to work. So we went the other route, which is running Hadoop in Docker containers, meaning that we create containers on the machines, the physical machines that I told you about, and we make them look like machines. So effectively, we're doing what a hypervisor does, right? We create virtual machines, which by definition are long running. So that machine could be up and running for 365 days because it's to the Yarn resource allocator, that looks just like a node. And we put the data node manager, the data node process of Hadoop in a container, and we put the node manager on another container, and we let them live on the same machine next to each other. So if we want to, we will launch another Docker container, and we put another node manager in it. So now we have 2 node managers running on the same machine. Or we can allocate the one that is doing the node manager to customer A, while the one that is running the data node to customer B. Remember, the reason, the motivation behind this was that we wanted to be able to share physical resources without compromising security, right? So if you have and actually I think I have a diagram for that. let me show you this. This is probably easier to look at when we talk about this. So this is your physical machine. And on this machine, you have your kernel and stuff, and then you have 2 containers running. If you look at one of these containers, it just looks like a machine. It actually runs /sbin in it. So it's as close to a real Linux machine as you can get. And it runs the Hadoop data node process, right? But because it's a container, it is isolated. All the disk resources that are allocated to this guy are isolated. This one does not see those. Neither the processing resources, nor the memory, nor the disk. And this one runs, it looks very similar to that guy, but this one runs a node manager. So if for some reason this machine is sitting idle, while it is holding the data of customer A in its data node, but there's not much processing because that customer happens to be in India, and it's nighttime for them, it's daytime for us, a customer in the US can run a node manager in this container and get things done without actually touching any of this data. Yes?
Just out of curiosity, so how are you managing the relationship between the data node and the master node? I mean, this container needs to communicate with the master node.
Yes, it does. So let's actually look at these 2 user interfaces. So how many of you are familiar with this interface? This is a typical Hadoop user interface. Good, well, about half. This is showing the data nodes of a cluster, right? That's the name node, which is effectively the guy who's sitting there managing disk space across all of these machines and doing the replication and all the good stuff. And these are the nodes that constitute the HDFS of that cluster, right? So you see the names are 201.19C01. This C01 in our convention, this is how we name the machines and containers. This is container number 1 on this machine, right? But those of you who are familiar with this user interface know that to Hadoop, this line is actually a machine, right? So we set things up so that from the point of view of that master, which in this case is the name node, this is just a machine. It has a static IP address. It does all the communication through its node manager process back to the mothership. There is no difference from the point of view of that guy between this and an actual physical machine. That's actually the work that we did to make sure that that guy cannot know that this is a container. And there's actually a reason for that. We have cases where we need to allocate physical machines next to containers to the same cluster for a number of reasons. The customer wants dedicated resources, right? Or some customers are more sensitive about the data. They don't want even a container that belongs to somebody else to run on that machine. So, okay, I'll give you a physical machine, but for your jobs, I'll give you containers. So this is designed in a way that from the point of view of the name node, which is what you call the master of the HDFS, the storage side, and the resource manager, which is the master from the point of view of resource scheduling, running the jobs, right? Hadoop has 2 major components. One is the HDFS for storing data. The other is the resource manager, which actually launches jobs to manipulate that data. Again, you see, to this guy, these are the machines that it sees. But if you look at the name, it's 205.35C02. This is container number 2 on some machine, which is this machine. So everything is engineered in a way that from the point of view of those master processes, these are just machines. So if you can achieve that, then they don't care. Just as when you add a physical node to a cluster, it starts talking to your resource manager, the container running the node manager process will do the exact same thing. That's why we had to jump through those hoops, the networking, the logs, all of that stuff, to make that container look just like a machine to the resource manager and to the name node.
Now, after this, how do you solve the
Well, so that was making changes to the capability. So you see, the problem is not that Docker is incapable of doing those things. It's that you need to do some strange configuration if you want to achieve those things, such as logging, such as static IP addresses, such as large MTUs for jumbo packets. So we had to go through the source code, and none of these are documented, to see why it does things the way it does, and compare that against against how the kernel on the Linux side manages the C groups and the namespaces to see what kind of configuration we should pass. And in some cases, we ended up making changes to Docker to do that. You actually, if you look at the commits done to the Docker source code, you will see code from our developers for those purposes. But a lot of that is configuring things in certain ways so that we can, for example, make sure that the log namespace is properly isolated across the containers. So I'm glad that you brought that question up, because as you see, these user interfaces show you that this is a Hadoop cluster with its name node and its resource manager, looking at these machines and working with these machines, while these machines are actual containers that have static IP addresses and everything that the resource manager expects to see. A few words about, well, we talked about some of these as I was answering the question. So on a typical machine, we do one data node container and one or more node managers. Now notice that when we look at this picture, this is a little bit deceiving because this shows you two containers that kind of sort of look similar. But those containers that I talked about in terms of the one that runs the data node and the one that runs the node manager are very, very different. Why? Because the data node process in Hadoop requires a lot of disks. Remember, it's your file system, right? Pretty much all of, not all, but almost all of the disk space goes to the data node process. But it doesn't really need a whole lot of CPU cycles. Node manager is the one that does the jobs. So it needs CPU cycles. It needs a lot of memory, but it doesn't need disk. It only needs a small amount of disks for scratch files and the shuffle phase and the intermediary steps of running jobs. So those two, the container that runs this guy and the container that runs this guy look very, very different. One of them has a lot of disks, a lot of CPU. The other one has a lot of CPU, a lot of memory, almost no disks. And actually, if you look at, so this is what you see here is login on the host where we're running the Docker container. So as you see here, this is the host, and I do a Docker PS, and what I'm seeing here is 4 containers. And if you look at the names of, now, don't mind these two, there's a separate reason for these two, but if you look at these two, you will see that the names of these Docker containers are actual host names, which are associated in our DNS with IP addresses and everything. So this is how the host looks like. If you log onto a container, so you actually SSH into one of those containers, and you, as you see, so uname-a, this is giving you the name of that machine, which has a C02 on it. So this is a container. You do ps-ef, you see spin in it. You see udevd running, you see sshd running, you see postfix, you see Nagios for monitoring, and you see syslogd for logging, right? So all the typical processes that you see on a host are running inside this container. This is where our usage and our workaround for these containers is very different from what you typically see in the world of Docker on the development side, because again, you bring up a container which has like one process or a process and a couple of its children, and it does something and it finishes and it's done. Here, we're running a container that runs spin init, which is effectively process number 1 on your machine. So this looks really like a machine. It runs SSHD, so you can SSH into that into that container, and you have all the processes that you need for this, including the node manager process of Hadoop. So to Hadoop, back to the point that we were just talking about, this is just a machine that is running the node manager process. No different than a physical machine running a node manager process. That's how the entire world of that Hadoop cluster sees this guy. But it's isolated. So some interest. Sure.
So you didn't have your own special kind of Docker?
No, we didn't want to do that. Like most open source projects, if you fork off of it and make a lot of changes, then the big problem that you're dealing with is that the community make changes and it advances and all that. We didn't want to do that. We tried to make sure that the key things that needed to be added, for example, there's this concept of user namespaces. Think for a moment about those two containers that I just talked about running on that machine and the user root of those two containers. Does the root in that container have access to the files owned by root on the host? You don't want to, right? Or how about the root of this container? Because root has certain privileges. And how do you prevent that root to access any files that might be owned by the root in this guy? So we needed to make sure that certain features are implemented, and we contributed those back to the Docker code. But with those aside, right now we're using vanilla Docker code. We are not making any proprietary changes to the Docker code. The proprietary side of it is all the configuration that we're doing around this. So the disks. This was another area that took us some time to sort of wrap our heads around, and how we wanted to allocate the disks. Probably the biggest thing that comes out of this slide is this one. So when you do stuff like what we just talked about, you want to make sure that your Docker containers do not see your Linux devices. You want to make sure that any disk space from the host machine that you want the Docker containers to use are passed to Docker as volumes. This is how you guarantee that a malicious process, if any, running in one container cannot even try to open a device to try to read stuff off of it, right? If you give device access and then something goes wrong in that Docker container, then you have no protection, right? Now, obviously, this is not a common case, but as a vendor providing service, we need to ensure that we prevent all of these things from happening, even in those unlikely cases. So no devices pass to Docker. You want to make sure that you create file systems on the host and just pass those as directories to your Docker containers. Also, the other pitfall here is that the default file system type that Docker uses is AUFS. I don't know if you're familiar with AUFS or not, but the beautiful thing about AUFS is that it's layered. So you can have files in different layers. If you look at this layer, you don't see certain files. If you look at this layer, you all of a sudden you see some additions. This is how it packages things. The ugly thing about AUFS is that it's layered. Because if it's layered, your performance goes down the drain. If you write to an AUFS file system, you get horrible performance because it needs to manage all these layers and decide which layer this data goes to and the blocks and everything. So you do not use AUFS for actual data. It's okay to use AUFS for installation of software packages like your root file system within that container, right? You do the installation once and then you do updates every once in a while. So who cares if it takes a little bit longer to update some stuff on the software side. But if your data is written to AUFS, then every single time that you're updating data, you're running through that stack of the AUFS code, which is horrible in terms of performance. So you want to make sure that you create volumes as ext3 or ext4, whatever typical file system that you use. And when you create those, you pass them as ext4 file systems that are now directories because they are mounted as volumes to Docker. If you're more interested on the Hadoop side, one of the things that we did, which is pretty important, is that across those 8 to 12 disks, typically what we do is that we create a small, on each disk, we create a small partition, and we put a file system on it, which is used by the node manager process, and then we give the rest of that disk, which is typically a very large file system, to the data node process. This is how we make those two containers look different in terms of the amount of disks that they have. And this way, you still have a number of small file systems that are given to the node manager container, so there's no single point of failure. If one of these disks fail, the other one's still working. And you also give a bunch of large disks to the data node process, which again, if one of those disks fail, the rest of them are still working. Networking. So we talked a little bit about this. Docker tries to allocate IP addresses for you from a private range. The only way that we could work around this effectively was to just completely, entirely disable Docker networking. Done, period. There's no middle ground, unfortunately. We tried to sort of make it allocate from a different range or work nicely with our routing protocols on the larger network, but it didn't work in the end. We ended up just disabling networking. Fortunately, Docker gives you a switch to just disable networking completely. And then we took over. So in our infrastructure, what we do is that we use Open vSwitch, which is a software-defined networking layer below Docker. So this is the host. This is Open vSwitch running on top of it, which acts as a bridge. And then the containers effectively create virtual Ethernet interfaces. This is what we do. And we create this little sort of tube. We put one end of that tube in the Open vSwitch bridge, and we put the other end of that tube in the container, and we make that an interface. So we do not use the networking that comes with Docker. And once we did that, we were able to easily, obviously, manipulate MTU for jumbo packets for larger transfers over the network. Before that, it was hard. Now, race conditions are very interesting in this situation. When you boot a machine up, and I'm talking about a physical machine, there's a certain order to the universe, right? Your BIOS goes through and probes your hardware, and there's interrupts, and then they kind of identify themselves up. And then at some point, your kernel boots in single user mode and gets those and starts creating devices for them. And then it goes to multi-user, and those devices can be opened by the processes that run on the host. So there's a very well-known process in terms of how, at the end of the day, the kernel running on a physical machine knows which devices exist on that machine. If you think about the Docker container that I just showed you, that Docker container is a process running on that machine coming out of nowhere, and we want to give it a network interface, and we want to give it a static IP address on that network interface. The problem is that order of probing and deciding which device goes where and all that does not happen in that process. You create a container and boom, you have a container. So what happens is, but then, let's go back to this process list for a moment. You run sbin init. Why do you run sbin init? Because you need some sort of process, a standard process launching mechanism on that machine that goes through the RC files and runs things in a certain order and brings up networking and brings up NFS and brings up this and brings up that, because you have a lot of automation written for those, and you create those scripts so that your host launches in a certain way. Problem is, because there is no order to things, you don't really know when your sbin init actually runs, for example, the networking code. And whether at that point, this virtual interface, the Ethernet interface that I just talked about, is completely active in that container or not, because you're injecting that into the container. So it's a matter of milliseconds, right? If you do it a little bit later, the networking code runs, and it doesn't see a network interface. Boom, you don't have a network. And good luck SSHing into that machine. So we needed to do some work to work around these race conditions. Effectively, we serialized the process of bootstrapping networking for the Docker containers so that things happen in a certain way. Basically, we induce that order. And when those are done, and we have a networking stack, then we transfer that networking stack, which is what we call, well, not we call it, it's in the kernel, the network namespace of that container, which is hand-built, into the actual container and run spin init on it, which guarantees that when spin init runs, the networking devices are all built and ready to be used. So you need to do a little bit of magic here to orchestrate the order in which things are created for that Docker container. Otherwise, you run into, the problem is that you run into issues that are not easy to troubleshoot, because sometimes it works, sometimes it doesn't, right? Out of the 10 containers that you launch, 8 of them work, 2 of them don't. Good luck finding out why. The other issue that we mentioned that is important to us is monitoring and metrics. Fortunately, you don't need to monitor the Docker process itself. We thought that we had to, but the fact is, if Docker process dies, the containers die, you will know some other way. So you don't really have to monitor it. You will know. However, from the point of view of Hadoop, there's this little piece of Hadoop that is called the health checker, which the mechanism Hadoop uses to decide whether this node is healthy or not, because it's a distributed file system, right? And it's distributed resource scheduling. It needs to know whether I should dispatch jobs to this machine or not. Should I send blocks to this machine or not? So it has its own way of checking the health of those machines. Now, because we sort of handcrafted that machine for Hadoop, we need to make sure that that Docker container somehow understands the health of the underlying host so that it can report it back to the Hadoop stack. So the neat way to do this, and once you figure it out, it's very easy, but the hard part was to sort of get to that point, is that whatever files that you're using to determine the health check of the machine, you can still run things on the host that go and check things and write to a file whether it's healthy or not, or write exit codes and so on and so forth. You can mount those files, you can mount specific files into your Docker containers and mount them in a certain location where the Hadoop processes that run in the container expect them to be there. So effectively, on the host, you're monitoring the health. And on the host, you're writing those files. But because these are mounted to certain locations inside the container, the Hadoop process that runs in the containers reads those and determines whether the node is healthy or not. So it just works very, very nicely. Metrics, thank Google. They did an open source project called CAdvisor, which is very nice. It runs on the host, because if we had to solve this problem, the metrics inside the containers, we had to do a lot of extra work. But they created CAdvisor, which architecturally is interesting because it understands the C groups data structures of the kernel. So it's a separate process that runs on the host, not in the containers. But using the data that it collects from the C groups data structure, which knows everything about the resource usage and the limits and everything that we have created for the containers, it actually mimics whatever metrics that you want to collect, how much memory it's using, how much network packets, how much disk space, the disk bandwidth. And then you can plug that into whatever you're using for metrics. We use Graphite. We use collectD, and we collect that data, send it off to Graphite. You just write a nice little plugin to talk to CAdvisor and get that data from CAdvisor. So in a way, you're bypassing the containers. You're getting this data from the host using CAdvisor, and then you just feed it into your metrics system. The only problem with CAdvisor is that the disk statistics is pretty weak. That's actually an area that we are doing our stuff, and we're contributing that back to the CAdvisor code, so it will be open source. And the beautiful topic of security. This is a question that comes up constantly, and there are a number of things. First of all, Docker by default runs in what they call the privileged mode, which means it has access to everything. You probably don't care about it when you run it on your laptop, but you do care about it when you run it in production. Now, you find out about it and you're like, oh, why, I should turn it off. You turn it off, all kinds of things start breaking, because the assumptions of a lot of tools around Docker is that it's running in privileged mode. So turning privileged mode off was not a straightforward task for us. So we had to go in and tweak a number of other parameters that we passed to the host to turn on certain capabilities in the kernel so that without privileged mode, it actually still works. And again, it's not changes to the Docker code. It's configuration that you do on the host so that Docker can still live in a world where it's not given enough privilege. So that's quite a bit of kernel tuning. Now, one thing that makes containers fundamentally different from hypervisors, and it could be its Achilles heel, is that containers share the same kernel. Remember the image that we had? Hypervisors, their own guest OSs. Containers, all part of the same kernel. What this means is that if you run into some sort of vulnerability that compromises your kernel, all of your Docker containers are exposed. Versus in the case of hypervisor, where if some sort of vulnerability is discovered or happens to one of those guest kernels, who cares? The other ones have their own kernel. So this is something that you should be aware of. Now, I get this question all the time. So are hypervisors safer? Not really. It's not like you get kernel vulnerabilities every day. They are very rare because there's so much built into the kernel as safeguards. But still, it's something that you should be aware of. You should understand the difference of the architectures so that if you run into a case like that, you know that your containers are all exposed. So you have to be vigilant about that. Similarly, obviously, if there are vulnerabilities about libcontainer, which is Docker's interface to the C groups and namespaces, obviously, like any other service that you use in your environment, and you follow and look for vulnerabilities, you have to be listening to the grapevine if things happen here. We have actually had a couple of cases where vulnerabilities were discovered in Docker. So another component in your infrastructure. Just as your hypervisor code could have vulnerabilities. Pluggable authentication modules, a feature of the Linux kernel that lets you customize authentication on a per process basis, does not necessarily work nicely with Docker. We found this the hard way. How? Cron stopped working. Of all things, you have a machine where your cron jobs are failing, and you start scratching your head, why? And the root cause, basically, which goes beyond cron, is that PAM modules, some of them, set certain things in the kernel data structures for being able to audit and track who's doing what on your system. And to prevent manipulation of audits, once they set those things, they do not let anybody else set those things. Now, when you run things on a physical host, all is good, you never notice that. But once you run these things inside a Docker container, remember that these Docker containers share the same kernel. That Docker container now goes and sets one of those things. Now, cron, which is your little application, unaware of everything, goes and tries to set that thing because it always does that. On a typical machine, you run cron and it goes and sets your login UID. You don't care, you don't notice. But this time, because it's running inside the Docker container, it goes there and it tries to do that. Oops, it fails because Docker has already done that. And the kernel underneath assumes that, OK, somebody set that. I'm not going to allow a second person to set the same thing because I don't want to allow somebody to manipulate my auditing data. So that is also one of those things where now, it's funny. If you do a search on Google for cron not working in Docker, you will be amazed. And you would think that the Docker people by now have fixed this. No. So there's no good answer to how you fix that. In some cases, you just disable PAM, because this is something you can do on a per process basis. In some cases, if you can't do it, then you have to make some architectural changes. But that's kind of an open issue right now. Delivery infrastructure, we talked about this a little bit. You have the Docker registry, which is how you deliver the Docker images to your to machines that want to run Docker. The problem with this is that it has very, very basic functionality. It doesn't give you any authentication. You cannot protect your Docker images. Docker just thought that, OK, I'm doing this public Docker registry, and then this is good for that. But if you run an enterprise service with multi-tenant environment, you want to protect those images. So effectively, you have to do your own layer of authentication on top of it. There is no caching. In a case like us where we have multiple data centers and we want to deliver these images, and these images can be big. It could be close to like 1 gigabyte of bits. And let's say you have 800 machines sitting in that data center, and every one of them wants to get that Docker image, do something with it. Now, all of a sudden, you're transferring 800 gigabytes, while you could have just cached that the first time that you fetched it. So you have to do your own layer of caching for that as well. And these are things that are built into pretty much every single web server that we know of. Apache does it, Nginx does it, right? So it's not really hard to have a registry that gives you authentication and some caching and just make your life easier. But again, it's not there. So you have to build those things yourself. And finally, orchestration. As I mentioned, initially there was none. Nowadays, if you look at the space, so Kubernetes and Mesos are both doing some sort of orchestration around Docker, which is nice, but it means that you have to run Mesos or you have to run Kubernetes. The company, Docker.io, launched something called LibSwarm. Hyperware, if you ask me. There's nothing behind it. I'm still, I believe they just raised $95 million. So let's hope that they finally do something with LibSwarm and make it a real package. So they sort of came out and announced this, but it doesn't really exist. What we're doing is that because Chef and Puppet are at the node level and they don't really do orchestration for you, we're using Rundeck plus Chef. So Chef does the node level stuff, Rundeck does the orchestration. We have some sort of glue code that does things here and does things here and sets nodes attributes here and then converges the node and make the container sort of materialize out of nowhere. But the significance of this compared to using something like Kubernetes or Mesos is that these guys are not only orchestrators, they are resource schedulers. Well, we already have one. We have Yarn. Yarn is very, very good at scheduling resources. We don't want somebody else to meddle with that. We just need orchestration. To the extent that we have worked on this, and this is actually the project that I'm working on right now as we speak, this seems to be a good compromise where you don't deal with the resource allocation stuff, but you have a good solution for node level and orchestration level in order to put things in order across your infrastructure in terms of when containers are created where, and when a container is added to a cluster, and when a container is torn down, and so on and so forth. And like I said, in our case, we're doing some in-house development around those, but those are the open source components that we are using. That was it. I'm sure there are other areas that if you talk to another operations person, they will bitch about, but that was my share of the journey of putting Docker containers in production. I'm happy to answer questions. Of course, I have to do the pitch. We are hiring, so remember this. And the technologies that we're using are sort of the leading edge, so come work with us. Yes, sir.
Are you going to open source that runtime plus
What is it that we're doing? Oh, are we going to open source that? We will probably, so what we're doing, part of it is plugins for Rundeck. Probably we will open source some of those plugins. But the parts that are proprietary are effectively the parts, because if you think about it, an orchestration system for this needs to have access to your inventory of machines and containers, needs to have access to your users and groups. So we have our own databases for these things. So there are layers that is proprietary data. The code that we're writing is by definition proprietary. It doesn't mean anything to open source it. But the plugins that we're writing, most probably we will open source them.
Thanks. On the security side, have you taken this through PCI audit? And if yes, did you have any issues with containers of different tenants on the same host?
We have not done an audit in that sense yet. So basically, we're running all the security tests that we're running against our physical infrastructure, against the same infrastructure that I described to you. But we haven't done a certification. In terms of differences, no, because by definition, the way we're doing this from the point, because we're running Hadoop on top of this, right? The way Hadoop is seeing this infrastructure is exactly the way Hadoop is seeing the physical infrastructure. There is no additional access anywhere in this stack that we need to sort of worry about when it comes to Hadoop. The area that we're more sort of cognizant of, and we're digging more, and this is not a story that is ended. We're still working on this because, and it's probably ongoing work, is the networking side and whether a breach from the lower levels of stack is possible into Docker. So far, it's been fine. I don't have any red flags to share with you, but who knows, maybe tomorrow I do. But nothing so far. Nothing so far. Yes.
So I'm trying to clarify, if I understand you correctly, the major benefit of running Hadoop node in container is you get the flexibility to move around the load manager. So in case one of your tenant require more tasks or computing resources, you can allocate it dynamically.
Exactly. Exactly. Now, I'm glad that you brought that up because moving containers around, it's nice to say it, but that actually requires a lot of steps. So a very good friend of mine at Google is actually working on what we call the checkpoint and restore of containers. If you actually go and search for Docker checkpoint and Docker restore, you will see it's very new code. I think it was merged into Docker 1.5 or 1.6, although I'm not sure. So he worked on using certain libraries to be able to kind of freeze a container that is running on a machine and then move it to another machine and resume that container from that point, maintaining all the TCP connections, which is not trivial, right? That's not what we do. We are taking advantage of the fact that Hadoop is a distributed system resilient to failure, right? So if I have to move a node manager from machine A to machine B, I just kill this guy here, I launch another one here, and this is what the orchestration layer does for me. Kill this guy, start this guy, add this guy to the same cluster. Hadoop just recovers from that. So that job failed, okay, no problem, I'll just resume here. So we are cheating in the sense that because Hadoop takes care of that for us, we're not really moving the container. We're killing, starting, attaching that to the cluster, and boom, everything works.
I'm curious if you can dynamically add more nodes for more jobs.
Sure, absolutely. So that's what we call compute bursting. So we actually do have customers that have jobs that run at certain times. It's customers that run jobs at certain times of the month. Customers that run jobs at certain times of the week. Customers that run jobs at certain times of the day, right? So they need more resources for that burst, and then they don't need the resources. Think of a customer that needs to do processing at the beginning of the month, right? Because they crunch and crunch and crunch and generate some reports. And then when they're done, for almost a month, they don't really do anything, or they do a little, right? So that is exactly the case. So when you have something like that, you can just launch containers on other machines and add those containers. This is, again, the job of the orchestration layer, right? Look at this schedule. This cluster needs such and such and such number of machines 2 days before the beginning of the month. So that is the schedule. And then you go and launch containers on 10 more machines, and you add those containers to the cluster. Boom, boom, boom. The customer runs the job, right? What happens is that they just get the extra performance. And it runs and runs and runs and runs, and 5 days later, they don't need that, and we know the schedule, and we just take them out of the cluster.
So you only add the node manager container, or you also add more data node container?
Good question. Well, if you think about it, data does not burst as much as compute does, right? There's sort of a pace to how data is added. And if you have a lot of data, it will take time to bring that data into your cluster anyway. So if you need extra storage, usually you know about it. Even if you don't know about it 2 months beforehand, you know about it a few days beforehand. And it's easier to add storage space to a cluster, because if you see that the rate of the data is increasing, you just add data nodes to it. Compute is the problematic part of this, because it can just go up like this, right? 6 o'clock in the morning, something happens, and then all of a sudden, all those MapReduce jobs start crunching data, and then they're done. So we need to be resilient in the case of compute. Storage, it's easy to manage. And, I mean, we're doing it, but it's easy. That's not the hard part. Compute is the hard part.
So the node manager and the data node container is not one-on-one mapping anymore.
Nope.
So they are flexible.
Nope.
Okay.
So you can have a cluster that has 5 data node containers and 50 node managers, just because right now they are doing a lot of crunching. And that's what, remember I told you about how we design all of the network stack and the infrastructure. So the reason that we can do this is that we have designed the network topology in a way that if you have 5 data nodes and 50 node managers, delivery of data on the wire to those 50 node managers is still fast enough. The throughput is there. The network doesn't become a bottleneck. On a typical normal network, that becomes a bottleneck. That's part of our expertise in making infrastructure that works nice for Hadoop.
Thank you.
Sure. Yes, sir.
So I have three questions. Last one's probably too far out, but the first one is who builds your containers and what distributions can they use, and what degree do you allow them using Cloudera, Hortonworks, or MapR, or those?
So we are lucky in the sense that we are a service provider, right? We don't offer our clients a distribution. We were just talking about this. We provide the service. So we go and pick the right components that work nicely with each other. So we use the standard Hadoop code from the trunk at a certain version. So for example, you have the resource manager, you have the name node and all that, and then you go and make sure that you pick the right version of Hive that works all the way with these things, and you pick the right version of Uzi that works all the way with these things. So we don't care about distribution. Fortunately, that's the one problem that we don't have to deal with, because we just provide to you the service. As long as you can come in and run your jobs, you don't care whether underneath it's Cloudera or Hortonworks or what. It's Hadoop. So you have Hive queries, you have standard Hive. You have Uzi jobs, it's Uzi, it works for you. The reason that those guys have to have their distributions is exactly that. They need to put things together so that things work with each other. And then they need to have other pieces of software to orchestrate how these things work with each other. So in our case, our job is not doing that distribution. It's making all of these work with each other and operate that. That's what we do.
So things like HBase aren't in the picture?
There are certain components that we do not offer. HBase actually is one of those. We do not do HBase. And to this day, I'm not convinced that HBase as a service is a very good idea. HBase is a wild beast. We do, for example, we do Spark, we do Flume, we do Uzi. So we look at what the customers are looking for. HBase is one of those that there is actually some interest in HBase as a service, but the problems that come with operating HBase are by far more complex than the value that it adds to a hosted service. So we're not doing HBase today.
So the second question is, when you deal with the containers, how do you manage the memory usage? Because like you say, compute can spike, and you obviously have to worry about their JVMs staying within the container limits.
So remember, I had on one of these slides next to my lovely Jim Carrey picture, isolation and resource limits, right? So the container support in the kernel allows you to set limits for your containers through C groups. And what we do is that on the slide that I was showing, Rundeck and Chef, we have written the Chef code so that when we provision the containers, we are setting the limits that we want to be set for these containers in the Chef node attributes. And then the code that we run on the host to create those containers, which effectively runs Docker and all the command lines and everything, passes the right values to Docker so that when the containers come up, they already come up with certain limits. So if the JVM inside that container runs out of memory, even though there is memory on the host, it will die. That's it. So we set the limits.
And I guess this is probably something you don't do, but do you use network block devices at all in your architecture anywhere?
No, we don't. We don't.
Yeah, I'm curious about how you're managing the configuration of things. Presumably you've got a base Docker image for various different node types. When you're adding one to a cluster, when and how do you pass in the configuration it needs to set itself up properly?
So, good question. There are two phases, if I may say, to that. One is the phase in which we build that image, right? So we have a process because we are dealing with physical machines and we are dealing with the Docker containers, and we also have some components in AWS. Actually, if you look at the diagram that I showed you, just because it's easier to manage here, this machine that people log into This is in Amazon, because we don't care about it, right? That's easy to manage. So, and we don't want to allocate one of those beast machines with gazillion bytes of this and all that to this use. So we are dealing with AWS images, instances, we're dealing with Docker containers, we're dealing with physical hosts, and in some cases we do have hypervisors actually, believe it or not. So we have a process in which we build a base image, and I'm not talking about a Docker image, a base image of an operating system and all the required packages, which is sort of the basis of the Altiscale software stack, right? And then we take that and we have other pipelines that off of that creates an AWS instance image and a Docker image and a VMware image and an image to image a machine, a physical machine. So basically, at one step, and this doesn't happen very often, every few months when there are certain changes, we go through this pipeline, and now we have images that if you launch a Docker container with it, or an AWS image, or a physical machine, they look almost the same. So we have delivered part A of the configuration to all of these. The second part is being done by Chef at the time that we create the container. So when we create the container, what happens is that you have the physical host, right? And we bootstrap that physical host against our Chef server. After these two are now friendly and they talk, we set a number of node attributes for this machine on the Chef server. Basically, we set things such as this machine is supposed to have 4 containers, and the IP address for these containers is such and such, and the network range for these is such and such, and the resource limits for these containers is such and such. And then we have a set of recipes, that's the bulk of our code, the automation code, that when that machine runs Chef client, is delivered to the machine, runs, looks at those node attributes, does whatever the configuration that we need to do, and creates the containers based off of those values. So part B of the configuration is done at the time of convergence.
So at the time that you're running Chef, you've got, so at the time that Chef is running, you know, for example, which customer those containers are going to be running on behalf of,
no.
Which cluster they're joining.
No.
Okay.
So now, it could have been nice to do that, but remember something. We are talking about a large infrastructure, and repeatability is something that adds a lot of value against a little bit of optimization, right? So what we do is that we build these things like cookie cutter in certain sizes, and they go into our container inventory, right? Now, when a cluster, the one that we were just talking about, needs some sort of compute bursting, we just go to the inventory. So the reason for this is that now we can build robots that do this for us, the orchestration layer, right? That's actually me doing this right now. So the robot goes and picks, looks at the capacity needed, and decides based on the existing inventory, do I need 5 containers or do I need 50 containers? And picks those, adds them to the cluster, and good. Now, yes, if we were able to size that on the fly, we could do this with a less number of containers, but the overhead of doing that in a large infrastructure is something that we just don't want to deal with. You had a question?
Maybe a naive question, but talking about containers on the Unix level, how does that jive with the fare scheduler and limiting resources at the resource queue level?
So that's actually a very good question. And people don't realize this, but let me go back to this picture because there is something, well, this is not containers. This is containers. This is a picture that conveys the message very nicely, but it's totally wrong if you look at how it's implemented. A container is not really something that contains a process. A container is a process, right? What happens is that your kernel limits a process in certain ways. And then we call that a contained process, right? So if you think about it that way, then you'll see that all of this scheduling is still happening. The kernel is still doing the scheduling for you. The container doesn't know anything about scheduling. It doesn't have to deal with scheduling. It just has certain limits, and it cannot allocate beyond certain limits and all that, and it's all fine and dandy. And if you launch a process and contain it, and then that process forks and creates other processes, and those fork and create other processes, all of that is still being managed by the base kernel. It just happens that those data structures regarding C groups and namespaces in the kernel are tracking all of those children in terms of who has access to what. So scheduling is taken care of. That's actually the beauty of, the one thing that I really love about how this implemented is that.
So one question is, how well do you see containers working with NUMA and sort of making sure you get the memory from the right node and right CPUs, etc. for performance?
I'm not really all that familiar with the issues around NUMA, so I'm not the right person to answer that question. What I can tell you is that in a way, containers are very dumb, exactly because of what we just talked about. It's up to you now, you being either the programmer that is doing that work, or whatever automation software that is making the decisions about how much allocation, what kind of limits, and so on and so forth, to make those decisions and allocate things the right way. If that right way is suboptimal, it's not working well. If that allocates, so it goes back to how intelligent the layer that decides about those allocation values is. If it's intelligent enough, it will do a nice job in allocating the right limits. If not, no. But on the NUMA side, I don't really know because I'm not that familiar.
Okay, I think we're going to stop it here. We'd like to thank our speaker again. Thank you, Nasser, for giving such a wonderful talk.
Thank you. Thank you.
And a couple other notes. Number one, I'd like to thank Yelp again for providing this lovely space. And what else? Our next talk is 2 weeks, is that correct? Our next talk is on the 29th. Chester, and it's here. Do you remember the talk topic?
Yeah, so our next talk is here. It's a two-speaker talk, and the first part is from Facebook, and they're going to talk about how they're using their machine learning stuff, and the other speakers from Ardeo talk about how they're using the machine learning in their music. So please join us.
Great, thank you, everyone.